Let's take a look at some examples now side by side of how we get from that exact step count or exact number of operations count to a big O runtime, or the order of growth. So here's a mystery function. Creates a new number, num1 equals num times 2, num2 equals num plus 6, and then return the sum of those numbers. So if we were looking at the exact number of operations, this is very similar to what we saw last lecture. Num times 2 is one operation, assigning it to num1 is a second operation, so that line is two operations. The next line, same thing, except it's addition, so still two operations. And finally, num1 plus num2 is an operation, and returning is an operation. So in total, we have 6 operations here. But when we think about just order of growth, we're going to take only the highest order term, so drop all lower order terms. And here, the highest order term is just constant. It's the number 6. And then we're going to get rid of any multiplicative constants. So really, this is 6 times 1. So we can get rid of the 6, and we just have constant runtime here. So big O of 1. The order of growth here is constant, or it is big O of 1. And I just want to point out here, notice that now that we've done this exercise, you can see, given that the number of operations doesn't depend on the size of n at all, we actually don't even need to count the number of operations. You don't have to come up with the 6. If you're asked for the big O runtime, or the complexity, or the order of growth, all those things are kind of synonymous, you can just see here that nothing here depends on the size of n. And so you can just say right away that this is constant runtime. So I'll point out something else here that you might have just noticed because we were adding things together. We have this law of addition, which means that when we have sequential statements, like in this function, def printing, this first thing here is a loop, and inside the loop, it's one step or one thing that you do. You print the item, and this takes big O of n time. And then you have another thing that is big O of n as well. So n operations, which is big O of n, it's linear. This is also big O of n. One thing that takes big O of n time, followed by another thing that takes big O of n time, is big O of n plus n, right? Because really, think about it back in just the operations, number of operations. Here there are n operations, and here there are n operations. So together, there are 2n operations. But notice something cool. Because we drop the multiplicative constants, this is still just O of n. And that should make sense because whether there's 2n operations or 4n or just n, they're all still lines. So the order of growth is still linear. So something linear followed by something linear is the same order of growth as just one linear thing. So we can take a look at an example here. Let's count the exact number of steps first. Take that approach. So answer equals 1. Or exact number of operations, I'll say. So answer equals 1, that's one operation here, assigning number 1. Then while n is greater than 1 and this n equals n minus 1 means this will loop n times. Inside of that loop, checking if n is greater than 1, that takes one operation. And then answer times n is one operation. Then saving that into the variable answer is one operation, and then n minus 1 is one operation. And storing into n is also one operation, and returning is one operation. So finally, we get 1 plus 5n plus 1. This is the same example we saw in last class. This is the number of operations. So one operation before, then this while loop, each time it does n greater than 1, which is one operation, and 4 operations in the body here that we can see, and finally returning 1. But if we look at the order of growth, or big O, our big O runtime here, big O of 1 plus 5n plus 1, well, I'm just going to add these together and simplify it, which we can always do. 5n plus 2, the highest order of growth term here is n, right? 5n, because 2 is constant time, whereas n is linear. And so we drop all lower order terms. So we drop 2 because it's a constant. And we can drop the 5 because 5n, 2n, n, those are all still just linear. So they're all big O of n. And so we get a linear runtime. This algorithm is linear, or big O of n. And I'll point out here that this example showed us the law of multiplication, which happens in particular when you have kind of nested things or things happening inside. So whenever you have a situation where there's some amount of work done here, and here for column in range length row, let's say that n is the size of our edges. Let's assume that the grid is a box, so a square, equal size width and equal size height, which is n. For column and range length row, well, the length of the row is going to be n, and so printing is one operation, and then accessing the value from grid is probably another operation. So let's say 2 operations, or even just 1, we're not sure. Either way, it doesn't matter how many we count. This is a constant amount of work inside that happens n times, and so this inner for loop is big O of n. It's linear. And this happens on the outside n times. And so a loop is linear, and each iteration of that loop here does n units of work, or big O of n amount of work. So we get big O of n times big O of n, because the outer loop is big O of n and the inner loop is big O of n. And that gives us big O of n times n, which is big O of n squared. And again, this should make sense from the perspective of thinking about how many operations are done. This print grid will get printed for each box in our grid. And if our grid is n by n, then we'll print out n squared values from that grid. And so that's where we get big O of n squared. So let's take a look at one last example here for the kind of number of operations. So if we're counting the exact number of operations, we have this outer loop for I in range n. So that happens n times. The inner loop for j in range n. So that happens n times inside of the outer loop. And finally, inside of both of those loops, we have print stir I plus stir j. Magic. We have stir I plus stir j, which is 4 operations. So converting to a string, let's say, is 1, then converting again is 2, adding is a 3rd, and printing is a 4th. And so in total, we have n squared times, right? In the outer loop, it happens n times. The inner loop happens n times per single value of the outer loop. So we get n squared total times that this gets called. And in here, the print stir I comma stir j takes 4 operations. So 4n squared operations total from just this segment up here. Then printing out these lines is 1 operation. And then down here for k in range n, print k plus 2. So here we're doing something inside of here n times, and the thing that we're doing is 2 operations. So 1 is adding 2 to k, that's 1 operation, and printing is another operation. So in total we get 2n operations from this loop down here. And putting that all together, we have 4n squared plus 1 plus 2n operations. Wow, what a pain to add all that up. Well, if we're looking at big O runtime, we take that and we drop the multiplicative constants and the lower order terms. So what's the highest order term here? The highest order term is n squared, 4n squared, because 1 is constant, n is linear, and then n squared is quadratic. And so we can drop the lowest, all the lower order terms, 1 and 2n, and we also drop the multiplicative constants. So we drop 4 and we drop 2. So n squared plus 1 plus n, and we drop the lower order terms. We get big O of n squared. So this is quadratic runtime. So notice it doesn't matter that we have this additional for loop here, because as n gets really big, the vast majority of the time is spent on this nested loop. Because it grows, the runtime that it takes to do this nested loop is way, way larger than just a single loop on its own when n gets really big. And so now that you've seen this, you can work backwards and figure out that you don't really need to count up all the operations in the entire function. You just need to figure out where the highest order activity is, where here it's a nested for loop, and that tells you that your whole function is big O of n squared. So to summarize here, big O is measuring the amount of time needed as our input grows, size n, how long our code will take to run. And we want to know about this asymptotic behavior, and I'll get back to that word later, of our problem as our problem gets really large. And we do this by focusing on the term that grows most rapidly. And how do we focus on the term that grows most rapidly? By ignoring all multiplicative and additive constants and lower order terms.